Welcome back to The Explainer. Today, we are taking a deep dive into the absolute engineering marvels that make reaching the stars possible. Because we aren't just talking about the rockets themselves, right? We're breaking down the massive, incredibly complex global launch systems that actually give those rockets the platform they need to fly. So, what does it actually take to leave Earth? Well, before we can even touch the vacuum of space, we've got to fight this invisible, relentless enemy right here at home: gravity. Beating gravity means producing enough continuous thrust to overcome an acceleration of 9.8 meters per second squared. And doing that, it takes way more than just building a really big engine. We're talking thousands of interconnected systems, pinpoint geographical precision, and literally building concrete cities solely designed for controlled explosions.
Okay, let's dive into this. Here's our roadmap for today. First, we'll unpack the anatomy of a spaceport. Then, we'll look at why launch geography matters. Third, land, sea, and air alternatives. And finally, we'll map out the future spaceport ecosystem.
Section 1. Anatomy of a spaceport. Let's start right at the ground level.
Now, what's really interesting about this slide is the sheer scale of the subterranean infrastructure that usually stays completely hidden from view. I mean, to really grasp how we get things like global GPS or satellite comms, you have to look down. Just look at the massive flame trenches sitting right below the pad. These are specifically engineered to channel away that violently extreme rocket exhaust, so the acoustic shockwaves don't literally tear the vehicle apart during launch. Right next to that, you've got cryogenic fuel storage farms holding liquid oxygen and rocket fuel at unbelievably low temperatures. Then, off in the distance, you'll find the integration hangars, where payloads are meticulously assembled, plus those massive transporter vehicles that just slowly, carefully crawl these multi-ton rockets right out to the pad.
Now, all of that massive infrastructure we just talked about, it exists to support one very specific, highly orchestrated timeline. Every single launch involves years of planning, and it all comes down to these final critical steps. First up, we've got the exhaustive pre-launch checks, verifying thousands of automated systems. Next is fueling, where those freezing cryogenic liquids are pumped into the rocket under immense pressure. Then comes ignition. The engines fire up while a heavy mechanical hold-down system literally clamps a highly explosive, multi-ton rocket right to the pad, which honestly is just as stressful as it sounds. Finally, only when maximum thrust is safely achieved we get liftoff, the clamps release, followed by the ascent phase where tracking radar and mission control step in to guide the whole thing into orbit.
Moving on to Section 2, why launch geography matters. Let's take a global view.
You see, you can't just pour some concrete in your backyard and launch a rocket. You have to play by the rules of orbital mechanics. It's kind of like jumping onto a spinning merry-go-round. By placing spaceports near the equator, take the Guiana Space Center in French Guiana, for example, rockets can actually harness Earth's rotational velocity. They get this massive free speed boost of about 1,670 kilometers per hour just from the planet's natural west-to-east spin. This rotational boost is a huge deal because it lets rockets carry significantly heavier payloads into orbit while burning way less fuel.
So the crucial point is that this creates a major strategic trade-off. On one hand, equatorial launches give you that maximum rotational speed boost we just mentioned that makes them absolutely ideal for throwing heavy communication satellites into geostationary orbit, where they just stay fixed over one single spot on Earth. But on the other hand, we have polar launches. These are often launched from places like Vandenberg, shooting straight north or south over the poles. Now, they get absolutely zero free speed boost from the Earth's rotation. Nothing. But because the Earth is rotating beneath the rocket, a polar orbit will eventually pass over every single point on the globe, giving you unmatched total planetary coverage.
And that actually brings us to a highly specialized type of polar trajectory known as a sun-synchronous orbit, or SSO for short. Put simply, this is an orbit that is carefully angled so the satellite passes over any given spot on Earth's surface at the exact same local solar time every single day. The sun is literally always hitting it at the same angle, which creates perfectly consistent shadows and lighting. And if you're wondering why that matters, well, it's precisely why military reconnaissance, weather tracking, and Earth observation satellites rely so heavily on SSO. It makes comparing daily images incredibly accurate.
All right, Section 3, land, sea, and air. Let's look at the alternatives.
And this brilliantly illustrates exactly how modern aerospace engineering is breaking free from traditional fixed coastal infrastructure. Because of those strict geographical limitations we just covered, we've had to get creative. So we've expanded from standard land pads to sea launches, using these massive floating ocean platforms that can literally just drive right down to the equator to grab that free speed boost. And then we've also got air launches. This is where large carrier aircraft fly way up high, completely bypassing bad weather, to drop and launch smaller rockets right in mid-flight.
If we use this as a quick reference guide to compare these systems side by side, you'll see that land launches are, well, they're still king when it comes to raw payload capacity. But they definitely suffer from low flexibility, because you obviously can't move them, and there's high overflight risk if you're launching anywhere near populated areas. Sea launches, meanwhile, offer excellent mobility and keep those launch paths safely over empty oceans. And then you have air launch systems. These completely maximize your flexibility. You can launch from virtually anywhere, entirely bypassing weather delays, and they carry the lowest overflight risk of all. The only catch is they're currently limited to much smaller payloads.
Let's move into our final segment, Section 4, the Future Spaceport Ecosystem. This is all about next-gen infrastructure. Let's move to the horizon and see how this builds into a truly vast, interconnected ecosystem. Because the era of massive, single-use rockets taking off from government-owned pads, that is rapidly evolving. Just notice how dynamic this future environment looks compared to the static concrete pads of the past. We are talking about autonomous offshore launch pads seamlessly communicating with hypersonic carrier aircraft zooming across the globe. You've got commercial space tourism terminals built directly alongside orbital gateways and reusable boosters executing pinpoint vertical landings right onto autonomous drone ships, ready to be inspected and flown all over again in just a matter of days. It's a total game changer.
Now, to support this incredible operational tempo, Spaceports are adopting some seriously crucial next-generation features. Let's rapid-fire through these. First, they're integrating renewable solar and wind power to minimize the environmental footprint of all these frequent launches. Second, they're implementing AI flight management for predictive analytics and safety. Third, real-time space debris monitoring is being hardwired directly into launch systems to safely thread rockets through our increasingly crowded orbits. And finally, perhaps most importantly, robotic fueling. Automated systems are replacing human hands for cryogenic transfers. That is a massive safety breakthrough that completely removes personnel from the blast zone while making pad operations way more precise. Altogether, this tech is making orbital access safer, far cheaper, and highly sustainable.
So we've covered the hidden depths of the launch pad all the way up to the orbital mechanics that guide our path to the stars. And the truth is, space access is democratizing faster today than at any point in human history. So I want to leave you with this to ponder. As autonomous offshore pads, commercial space tourism terminals, and hypersonic spaceplanes become our actual, everyday reality, where will your journey to space begin? Thank you so much for joining me on this explainer. Keep your eyes on the skies, and I'll see you next time.